Hi there, physicists. It's Mr. Clegg. Welcome to talking about displacement, distance, velocity, and acceleration. Hopefully, we'll give you a pretty good overview of all this. So, displacement is a vector that points from the origin, which is whatever point we choose to be the origin, and to the object in question. So, for example, in this example, here's my origin. I put a little star on the ground during class, and I walked along a square 1 meter, and then I walked along a square 1 meter. And then when I got to this location, my displacement vector was square root of 2 meters because it's the distance from here to here, which is the hypotenuse of this triangle. So, um, and when I go back to the origin later, my displacement returns to zero. So it's just a straight line pointing the shortest distance possible from the origin to the object. And no matter where you go, it just points that direction. Another way we could visualize this is, let's say this is our displacement vector. Here's our origin. As you move around, that displacement vector just keeps pointing to wherever your location is. So that's just a way to visualize it. Okay, go back to the other thing. Come on, pause. Okay, so the other concept here is the distance, which is the total distance traveled, and this is like the odometer in your car. So in my example in the class, when I went around the square, I started up here, I went 1 meter, I continued on, my total distance was now 2 meters. As I continue around, 3 meters, 4 meters. By the time I got back to my distance got to be 4 meters by the time I got to the origin again. But again, the displacement went 1 meter, and then displacement also has a direction. So it's 1 meter to the north, square root of 2 meters to the northwest, and then it became 1 meter again to the west, and then less and less, and now became zero again. So hopefully that makes sense. Yeah, I already said this. So if you were going in a path, the shortest distance along the path would be your displacement. That's how far away you are. And again, that can return back to zero. It's kind of like a stretchy rubber band. It can go back to zero if you go back to the origin. But the distance never decreases. It always just increases the farther you go. So that's like the odometer of your car. Okay, now we're going to keep going and we're going to talk about average velocity. So the average velocity, and this bar above means average, is defined as the difference between 2 points, the second point minus the first point. And I know we're used to putting x on the horizontal axis, but here we're going to do it on the vertical. So we actually have this is my position in meters. Position is given by x sometimes other letters, but we'll use x for now. And the units are meters. So the 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 distance between x1 and x2 is 2 minus 1. So you take the second one minus the first, and that's my delta x, right? Delta means second one minus the first one. And my time 2 minus time 1, that's my delta t. That's how much time went by from the second one. Sorry, from the first time point to the second time point, take the second one minus the first to get that difference. And so the hopefully you can see that delta x over delta t, that's the slope of that line. So that's the rise over the run. And so the slope is the average velocity. And again, average with the bar over it. Now, if we want to find out how fast something is going at a certain moment, we can start to make the average velocity time interval smaller and smaller. So here we're putting T1 and T2 closer together until now we have a slope that shows the speed at this exact moment in time. Instead of two different moments in time, those two became one. The mathematical way to say this is we're taking the limit as delta t approaches zero of delta x over delta t. So we're taking the average velocity, delta x over delta t, we're taking the limit as delta t gets closer to zero. In calculus, that's actually called taking the derivative. So I'll show you that in just a second. As delta t gets smaller, the slope gets closer to the instantaneous velocity, which is the slope of the tangent line. That's another word there. The tangent is the line that touches a curve only at one point. And so instead of 2 points being connected, I think that's called a secant. I might get the wrong word for that, but I think it's called a secant. But now we have a tangent line. And in calculus, this limit as delta x over delta t, as delta t goes to zero, that limit is actually called the derivative, and we say dx dt. If you're not in calculus, don't worry about that. Just know that that's a thing that exists. Okay, acceleration. Now, acceleration is the change of velocity over the time elapsed. And so average acceleration is sorry, that's the average. I forgot to say average. So we have the average acceleration, bar over the top, is velocity 2 minus velocity 1 over t2 minus t1, and it's equal to delta v over delta t. Now, I decided not to do it, but I could have made a graph that looks exactly like the one we just did, but instead of x up here, we would have velocity, and this would be meters per second instead of just meters. And the same exact picture would apply uh, for acceleration. You're just taking, connecting the 2 points, and it's the slope of the secant segment that's going between those 2 points. And then as you bring them closer and closer together, we can get the instantaneous acceleration, which is the acceleration at a certain point, the change in velocity over time at that exact instant in time. So in calculus, if you're in AP Physics C, you can do the acceleration is the derivative of the time derivative of the velocity, and it's also the second time derivative of the acceleration. Sorry, said wrong. Second time derivative of the position. There we go. Acceleration is the second derivative of the position. That's what I meant to say. Okay, so here's a couple notes. Acceleration and velocity are vectors, and as such, they're always positive with a little asterisk here because we make an exception. So they're always positive, and the direction is specified by an arrow or words. Exception. Sometimes we reduce vectors down to an axis, such as the x-axis, and we say it's positive in one direction and negative in the other. And then if that's the case, it'll be specified, but we're not drawing arrows anymore at that point usually. This can get a little confusing about is it always positive or not, but hopefully through the examples, we will get it straight. So now we're going to talk about the directions of the velocity vector and the acceleration vector. We already talked about the direction of the displacement vector. It always just points to where the object is. Now the direction of the velocity vector always points in the direction of motion. So we've got this little ladybug here going this way. The velocity points that way, going this way. These ladybugs are all going in different directions. The velocity vector points the way that they're going. If it's a longer vector, it means it's going faster. If it's zero, it means that it's not moving or at rest. Okay, I'm going to just pause here for a second and show a little app. See if I can do this. All right, here we are. I just switched over to another screen where we have fet.colorado.edu, and there's a simulation called Ladybug Motion 2D, and you can search that up. You might have to uncheck the place where it says HTML5 to be able to find that. In any case, because it's an older app, it's not written in HTML5, so you have to do it. So here, once you get this thing loaded up here, you can click on the center, and we're going to do the top version here. Run ChirpJ browser compatible version. Hopefully that works. Yes, it's working. And we have to wait for the thing to load. Takes a little bit of time. Okay, now we are setting it up. Well, this does take a while. Okay, so now we have this thing. One of the things that you can do, you can control the ladybug with the remote control. And one of the things you can see is when I just specify a displacement vector or a position vector, same thing, it actually just moves it to a spot. And you can see there's these other vectors that are coming out. What are those things? I'm going to switch it over to velocity now. If I give it a certain velocity, you can see that the velocity just always points in the direction. Now can you see why I made my diagram green on the other one? Because velocity, now if I want to make it fast, the velocity has a longer arrow, right? If I want to make it very slow, the velocity has a shorter arrow. So that's pretty simple. But look, what's this pink thing that keeps shooting out? That's an acceleration. It has a very large but short-lived acceleration. And it's pretty hard to see what that value is. It's even hard to read it. But if I switch to acceleration here, now it's hard to control. Oh boy. It's a little bit hard to control here. Hopefully I can show this and you can see here we go. I'm going to make a circular one. This is a little easier here. So you can click on this guy up here to make. So a circular acceleration shows that what would it be like if the acceleration and velocity were at right angles to each other, perpendicular to each other? What would it be like if they were not exactly at right angles to each other? You can study these things. I don't know what's happening here. Linear. Oh, linear is not, I don't know what that does. Anyway, it's a little bit hard to control, but you can sort of try to see what happens when the velocity and the acceleration are in opposite directions, right? If they're in opposite directions, what's happening to the speed? What's happening to the speed? If they're in the same direction, what's happening to the speed? Right? So a lot of times they're in the same direction. Okay. And now they're in opposite directions. It's a little bit hard to make them exactly in opposite directions. I wish I could make them exact, but after you play with that for a little while, hopefully you can see pretty soon some patterns. And here's what I'd like you to notice is that if acceleration and velocity are in the same direction, the speed is increasing or speeding up. If they're in the opposite direction, the speed is decreasing, they're slowing down. So that means that the velocity vector is getting shorter if they're in opposite directions. If they're at right angles, then they are turning. The ladybug is turning left, turning right. I hope you can see that this is the same thing as this, but turned around, it's rotated a little bit. But here's a right turn. Here is a left turn. Now, you can do more than one at the same time if we are going both forward. Let's say our acceleration is forward and to the left, then we're turning left and increasing the speed at the same time. This would be like if you were turning your car to the left and pressing hard on the gas to increase your speed at the same time. Then if you are turning right, for example, and hitting the brakes at the same time, then you'll be slowing down and turning right at the same time. The acceleration will be back and to the right. Hopefully that makes sense. Anytime there's any component in the same direction, you're speeding up, opposite direction, slowing down. And if there's a component that's to the side at all, you are turning. And if you could be doing both at the same time. That covers all the possibilities for when there's an acceleration. Now, when there's no acceleration, there are two options. Either we are totally at rest, like we're just chilling, no velocity, no acceleration, the object's at rest. Or you could have zero acceleration when the object is moving at a constant velocity. Let's just take a look at that option here. So, whoops, I'm going to go back to velocity here. Whoops, let's see if we can, what's going on here? It's not working. So I'm going to reset all the settings. We're going to go to velocity. Okay. Oops, come on now. There we go. So when I give it a constant velocity, there's no acceleration. Now, if I change the velocity, it has to accelerate in order to change. So you can see there's a very short-lived pink acceleration arrow that comes out, but now there's no acceleration because we're just moving in at constant velocity. Okay. Back to the notes. That concludes this lecture, but I'd like you to look at examples 2.3, 2.4, and 2.5 in the Giancoli book, pages 24 to 26. All right, I'll see you guys in the next one. Look forward to it. Okay, bye.